Let's see this theory in practice, and we have here an example. So in this example we are using a sampling rate of 44.1 kilohertz, and we will have a sine wave that has a frequency of 400 hertz and 1 second duration. So we need 44,100 samples and 400 periods of our sinusoid in this second. So here we are using Python. I'm importing NumPy. Here I'm defining the sampling rate. Here is the frequency of 400 hertz, and there are two ways we can build the signal. What I'm doing here first is called S, is the sine. So here's 2 pi f, so this is omega. The angular frequency is 2 pi f, and here we have this. This is our time, so it goes from 0 to 1 second in intervals of 1 divided by the sampling frequency. So this is our period, 1 divided by sampling frequency, and we have this sine wave. But we also can define our normalized frequency. So this omega is the angular frequency divided by the sampling rate. So we have the angular frequency is equal to omega is equal to 2 pi f. So this is what we're doing here, and we are dividing by the sampling frequency, and now we're having the sine of the normalized frequency, and here we have our time in terms of samples. So it goes from 0 to 44,100 samples. That means it's 1 second and in steps of 1, so it's n is equal to 0, 1, 2, 3, and so forth. And here we can hear our signal. So this is 1 second. This is our sine wave at the sampling rate of 44.1 kilohertz, and this is 400 hertz sine wave frequency. So if we plot the first 1000 samples, so here I'm plotting the both signals just to prove that they are in fact the same. So we have our sinusoid, the first 1000 samples. Now what we can do, we can multiply this sine tone signal with a unit pulse strain. In this case we are going to use a factor of n equals to 8. So here we are generating the unit pulse strain. So first I'm defining an array full of zeros, and then I'm inserting a 1 into every n equals to 8. So the multiples of 8. So what we have here is this unit pulse strain with zeros in between them. So there's just this our array of zeros, and I'm inserting a 1. So here what we have, a 1, then zeros, then another 1, zeros, and then we can listen to this unit pulse strain. So this is how it sounds like, and we are now multiplying our signal with the unit pulse strain. So this is what I'm calling here SDU, so our signal times this unit pulse strain, and this multiplication is also called the frequency mixing, and we can plot the result for the first 100 samples. So this is our original signal in blue, and we had sine wave. Now we're multiplying this signal with this unit impulse strain. So we have multiplying with this, and what we have is this downsampled, still with the zeros on. So when we multiply, we get this in red, and we have here, this is the downsampled version with the zeros on. So this is our signal still with the zeros in it, and we can take a look at the magnitude spectrum in dB. So here we have the magnitude spectrum of the original signal, and we have this magnitude here. So this is the normalized frequency, and this is the magnitude in dB. So this is what we're doing here. We're using FracZ to have this frequency response of our signal. So this plot shows the magnitude of the frequency spectrum of our signal, and we can observe that this is normalized frequency. So in this case, the Nyquist frequency is equal to pi, so it's 3 goes until 3.14, and it means that in this case is 22,050 Hertz, so it's half of the sampling frequency. So our sinusoid should appear as a peak at the normalized frequency of 400 Hertz divided by 22,000 times pi, and we have this value here, 0.05, and indeed if we look here we have approximately here 0.05. And now we can compare this to our signal with the zero, so it's the SDU, and we are plotting here now is the normalized frequency and the magnitude frequency response of the original sinusoid and the sinusoid with zero. So in blue we have the original, so it's the same as this one here, but now we have this downsampled version with the zeros on, and we have this one in orange. So it's very interesting to note that now we see that we had as our 400 Hertz tone, but also we have 7 new aliasing components. We have 1, 2, 3, 4, 5, 6, 7. So we go from the blue to the orange, and observe that always two aliasing components are close together, and this is because that the original 400 tones also has a spectral peak in negative frequency at minus 400, so it's a normalized frequency of minus 0.05, and this is why they are appearing here together, because here we would have in the negative frequencies also a peak. This is a characteristic of the sinusoid, and we see now we can also listen to the signal still with zeros. So we hear that it's quite different from our original signal because we have this is the unit pulse. This is our original signal. So this is our original 400 Hertz. We multiply with this unit impulse train, and what we get still with the zeros on is the downsampled version, and we have this 400 tone and 7 new aliasing components.